speaker. Welcome everyone to Wednesday Night at Lab. I'm Tom Zinnan. I work at the UW-Madison Biotechnology Center. I also work for the Division of Extension, Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight it's my pleasure to introduce to you both Catherine Jackson of Oxford University and Tracy Drier of the Department of Chemistry. Catherine's going to be up first, so I'm going to ask her the 5 questions. She braces herself. Catherine, where were you born?
Liverpool.
And what is the demonym of Liverpool?
Liverpool.
We got nothing.
Also known as Scouser.
And then where did you go to what we would call high school?
Liverpool.
In Liverpool. And then where'd you go for your undergrad degree and what did you study?
I studied natural sciences in Cambridge.
And then where'd you go for your advanced degrees and what did you study?
I studied PhD organic chemistry in Cambridge, teaching qualification in London, master's degree, history of science, and PhD as a historian, also in London. Yeah, that's it.
I studied inadequacy. And then you were here for a while at UW-Madison?
Yeah, I spent a wonderful nearly 5 years here in Madison in the originally History of Science department, then the Department of History, between 2015 and 2019, when I moved to my present position in Oxford.
Way to go. I appreciate it. Tracy, where were you born?
Michigan,
And where'd you go to high school?
Holland, Michigan.
And where'd you go for your undergrad and what'd you study?
Paper engineering in Kalamazoo, Michigan, Western Michigan.
And then you did some special program in glassblowing.
There's a small community college in southern New Jersey called Salem Community College that has a scientific glassblowing program.
And then when did you come to UW-Madison?
2000.
22 years of bliss. Looking forward to this. It's a great pleasure to have you both here. It's wonderful to have you back. Please join me in welcoming both Tracy Drier and Catherine Jackson to Wednesday Night.
Thanks, Tom, for the fabulous introduction and to all the people who have supported the event this evening. It is a real pleasure to be here, and thanks to all of you for turning out and joining this journey to the intersection between chemistry and glass into the microheterotopias of our title. What do I mean by microheterotopias, and why the new word? Well, I borrowed something and given it my own spin. The word heterotopias refers to spaces that mirror the world around them, but in unexpected ways. It's useful in thinking about places like hospitals that challenge our experience of the world, our immediate experience of the world, or labs, organized social spaces with their own routines and hierarchies, like the world outside in some ways, but utterly unlike it in others. As I learned about how past chemists worked in glass and why this was essential to the laboratory reasoning underpinning their research process, I came to understand the spaces they use as heterotopias. But these heterotopias weren't just smaller, they were where chemists learned to see a micro world of three-dimensional molecules. That's why I coined the term microheterotopias to highlight those spaces inside glass where chemistry was made to happen and chemists produced the molecular view of matter that we take for granted. This talk explains where microheterotopias come from. When and why did glass become the medium of chemistry? What were the consequences of that change? But it also highlights a remarkable continuity in chemistry's relationship to glass. Even though chemists use other materials alongside glass, we'll see that chemistry is still the science of building and managing microheterotopias. Every time a chemist builds glass apparatus to manage processes of reaction and purification, the space inside becomes a microheterotopia in which molecules are being manipulated, whose otherness is based on the extraordinary control and flexibility that chemists gain by working in glass. The connection between glass and chemistry is a powerful one. It's also deeply historical. There's no mystery as to why the ASGS logo displays the tools and skills of the scientific glassblower, but you may be slightly more surprised by the ACS logo. When Tiffany were asked to create a logo for the American Chemical Society in the early 20th century, they placed this piece of glassware at the heart of their design. Some of you may recognize this as Liebig's Cali apparatus or potash bulbs, a device for measuring the carbon content of organic compounds. But why did Tiffany feature glass, and why this item in particular? Is Liebig's Cali apparatus being used to analyze organic compounds? Its job was to trap carbon dioxide by dissolving it in potassium hydroxide solution. The sample burned, releasing water vapor trapped in this carbon calcium chloride tube and carbon dioxide. Dissolved carbon dioxide increased the mass of the Cali apparatus, and by measuring that increase in mass, we could calculate how much carbon was in the sample. Now here's a curious thing. Liebig invented the Cali apparatus while trying to measure nitrogen in drugs like morphine and quinine. That attempt ultimately failed. Measuring nitrogen turned out to be a lot harder than Liebig anticipated. And if you're wondering why Liebig believed measuring carbon could help with nitrogen, you can read that story in my book. Next 4th of July by the MIT Press. That was the first of several utterly shameless plugs. The key point for now is that the Cali apparatus also made carbon determination a lot easier. Not more accurate, but faster and crucially cheaper, because Liebig made the Cali apparatus himself by glassblowing. Using homemade glassware that was much smaller than the equipment chemists had previously used was destined to change chemistry. Because he wanted to control a new science of organic chemistry, Liebig taught students in his Gießen laboratory to use the Cali apparatus. And because other chemists wanted to make and use it, they began learning to blow glass. That's how Liebig's Cali apparatus drove what I've called the glassware revolution, chemistry's move into glass during the mid-19th century. Excellent.
Did I just forget?
It's okay. Fine. Moving into glass transformed chemistry, and the Cali apparatus became iconic of that change. Working with small, cheap apparatus meant more people could do chemistry. It also changed what chemists could do, beginning a period of extraordinary innovation in chemistry's methods and tools. This was the age of microheterotopias, and it changed not just chemistry and glassblowing, but physics and physiology and other sciences too. Now here on the left, you've got a rough plan for the talk today. Grappling with the organic world pushed chemists towards new reliance on glassblowing skill. As the discipline grew, they also sought results that retained their meaning when shared. This tension between innovation and standardization created the scientific glassblower, and it set a new model for collaboration between scientists and glassblowers.
Until now, the history of scientific glassblowing has focused on late 19th century high vacuum physics. Tracy and I are here to tell you that it all began in chemistry, that chemistry was the first precision science in glass, and to show you how chemists and glassblowers build the microheterotopias that make chemistry work now and in the past. We have two highlights. The first explains the origin of standard glassware items that chemists use to build component systems, forerunners of modern taper joint glassware, what we Brits call quick fit. The second shows how chemistry and glassblowing together solved the problem of identifying organic compounds, establishing melting and boiling points as so-called constants of nature. When you see how those things were done, you'll understand how microheterotopias changed chemistry and why they still matter today. This picture of a Kali apparat being weighed illustrates one way that glassblowing skill improved results. Now remember that the Kali apparat didn't intrinsically produce better results than previous methods. But when the glassblower Carl Ettling made Liebig's original into a smaller standard device in 1833, it could fit inside this analytical balance. And that did make weighing dissolved carbon dioxide more accurate. A device like Liebig's Kali apparat could also be used in new ways. The chemist Friedrich Wöhler sketched this apparatus in a letter to Liebig. Wöhler believed that Liebig's original problem, measuring nitrogen, could be solved by converting nitrogen to ammonia and dissolving ammonia gas in a Kali apparat containing hydrochloric acid. It was a very simple idea, and it didn't quite work. But one of Liebig's assistants, Heinrich Will, was a skilled glassblower. Will altered Liebig's original design, and his student Franz Fahrentrapp developed the chemistry. Published in 1841, theirs was the first reliable method of measuring nitrogen, and it remained so for half a century. Will and Fahrentrapp's apparatus shows how effective small changes could be. It differed only slightly from Liebig's original, but those differences were crucial to how the new device functioned. Because ammonia dissolved very readily in hydrochloric acid, Will and Fahrentrapp's Kali apparat could have a more open form, but that solubility also increased the risk of suckback into the hot combustion tube. Hence this large bulb near the furnace. Glassblowing made it possible for chemists to make and adapt apparatus to solve experimental problems. Scientists also ran into problems that only a skilled professional glassblower could solve. That's what happened in 1850, when the Bonn mathematician Julius Plücker began experiments to measure the magnetic properties of gases. One of the gases he hoped to study was carbon monoxide. But when he prepared it, he couldn't remove contaminating carbon dioxide, even by passing the gas through Liebig's Kali apparat. That was a serious problem, because the presence of carbon dioxide would invalidate his results. What could he do? Well, very fortunately for Plücker, the glassblower Heinrich Geissler had recently set up his workshop in Bonn. When Plücker approached him, Geissler knew just what to do. He converted each of the 3 bulbs along the base of Liebig's device into a bubbler. So into these 3 bubblers, creating a microheterotopia that controlled the flow of carbon dioxide, dissolving far more than Liebig's original. Thanks to glassblowing and chemistry, Plücker's experiments could proceed. And with the help of another of Geissler's inventions, a high precision balance made entirely from glass, he completed his investigations. This began Plucker's collaboration with Geissler, work that transformed thermometry, produced Geissler's eponymous discharge tubes, and created the new field of high vacuum physics. Philosophers still debate whether chemistry can be reduced to physics. History answers that question here with a resounding no. On the contrary, this example shows that chemistry and glassblowing were combined prerequisites for some of the most important developments in 19th century physics. Chemistry drove advances in physics, not the other way around. Geissler's Caille apparatus illustrates the link between skilled making and useful results. This was the driving force behind the origin of the professional scientific glassblower around 1850, 2 decades after Liebig introduced his Caille apparatus. Working with glassblowers was essential to the laboratory reasoning chemists used to stabilize formulae and to build useful theories of constitution and structure. Men like Geissler enabled the development of 19th century chemistry, very much as Tracy works with chemists here today. The rise of professional scientific glassblowing was partly a response to chemistry's need for improved functionality, but it was also vital in managing glassware innovations. Working in glass made it easy to modify apparatus, but for chemistry to thrive as a discipline, people working in different places had to be able to produce the same results. This meant using standard apparatus, and it introduced a tension between innovation and standardization that glassblowers helped manage by selling standard glassware items. Here are some of the Caille apparatus-like devices sold by Geissler's successor, Franz Müller, in 1904. These are microheterotopias, spaces within glass where mixing and separation are minutely controlled. All fulfill the same function, dissolving a gas in the liquid, but each was designed for a slightly different context. You can see these two on the top left were used in studies of respiration. Here is Geissler's device on the top right, and here below it is a variant introduced in 1900 by Wetzel and first sold by the Berlin glassblowing firm of Warmbrunn and Quilitz. Now, Wetzel found that even Geissler's device didn't completely absorb carbon dioxide, so he modified it to solve that problem, introducing this disc shown here in this diagram. That's a floating disc, so here's a replica. Okay. Maybe you can already see how that worked. Don't worry if not, all will be explained. The point is that glassblowers work to precise specification, exactly as happens today when you buy something from Millipore, Sigma or Fisher. Apparatus sold by 19th century glassblowing firms was always the same, no matter who bought it or who made it. That's how commodification supported laboratory standardization, making it possible for chemists in different labs to exchange and confirm results. The rise of scientific glassblowing firms changed how chemistry was done in one final important way. During the late 19th century, glassblowers began incorporating glass joints into standard glassware so that these could be connected to form airtight systems. This apparatus was used by plant physiologists studying carbon dioxide assimilation, and it exemplifies the combination of glassware components to form new microheterotopias in chemistry and beyond. Now, for our first performance this evening, Tracy is going to build a microheterotopia, placing the floating disc inside Wetzel's Caille apparatus. Over to you, Tracy.
So when I first saw this schematic, I had no idea what I was looking at. is this a solid shelf? Or is it floating? There was nobody from that time period to ask, and luckily, the Zoology Museum had a sample that we could look at. And we saw that in fact it was floating. So what I'd like to do is build one of those, like Catherine said, and to do that, these are the parts that I'll use. This will be the main body. This will be the piece that goes through. This will be the floating disc. This slides up and down through this tube. And then this will be the side arm coming out the side. So I'll start by making a mark 50 millimeters. And what I'll do is just float the tubing on the flame, the top of the flame, and when I get that little band of red, I'll just start to push it together and make a little rig. Always rotating. Always rotating. Always. So, for the sake of moving this program along, normally I want to make all my small parts ahead of time so that as I begin, I can just put it all together as I go. I would now flare this piece, let it cool, and cut it short. And you can see right in here that I've got a couple pre-made. So I will now close this end off, pull a little taper, and then I'm going to pop a hole. And I'll pop a hole so that this just rests in the hole and not go through it. One thing I'd like to talk about is as we heat glass, it softens and it constricts. That's a feature that really comes in handy, and depending on how things go this evening, we'll be using that. And as we do, I'll bring it up because that's a really handy thing, let's just say. So you can see as the heat penetrates through there, it's softening up, it's gathering up, heavying up. And so now I can just come in and touch it, bring it back, always rotating, bring it on center. Now I'm going to just slowly separate it. Best we can, we want to keep everything on axis. So now what I'm going to do is blow the hole. So I've tightened my fire up, smaller fire, angle my tubing. So I'm just getting that tip come out. Blow. Okay. So now I'm going to do it again. So now this is actually quite thin. But now you can see that there's a hole in there, which is what we want. Now we've got a bunch of debris, let's just say, on the edge, and I'm just heating up that rim and peeling that off so that we have a nice clean edge. So now we'd like these two to fit a little nicer than that. This hole is just a little on the small side. We'd like that ridge to nest in there a little nicer. So we're going to heat that opening, come in with a graphite and just lightly lift. If we overshoot, it's gonna go inside, and that's not gonna be a problem. So that's what we're looking for. You want to put a cork in the bottom, because when you're going to blow, you need to have something to blow it in. So now I just press these two pieces together in the fire. As that starts to soften and shrink down, I'm gonna just help it along the top here, and I'll blow. Okay, there's no hole. There's a hole. You just stop right now and fix it. It's part of the process. So now I just beat that seal. When I stuck those pieces together, you know, even right now, these pieces are stuck together, but if I were to drop this or hit it sharply, this would fall into a couple of pieces. So I need to keep heating this until these two pieces become one. Always rotating as I do this. You can see that inside tube kind of flop around. I'm not particularly concerned with that because we'll straighten it at the end. As it starts to constrict down, I'll stop and re-inflate it. Okay, now I'm going to get that centerpiece on center, and then I'll come back, soften the other side, and get everything on center. Now I'm going to create the shape of the piece here. You don't want it to just look like a tube. It's got a little bulge on the top and it tapers down beautifully to the bottom. So that's what we're going to recreate. I heat a section. Blow it up. Now do that once more here. I can see things got a little out of whack in the center there, so I'll just keep that seal. Straighten it. Straighten the other end. So now I'll take one of my discs. It's a little bit like the penny in the bottle or the skip in the bottle. You just take it. Slide it on there. Just like that. So now we'll continue. So now you'll notice that my hand is probably in front of the camera, but I will be tapering this down. I have to keep that end down because I don't want that disc dropping into the molten glass. So now I'll just stretch it down. And draw it off. So now I'll take time, round this off, pull some glass off, get it close. . I won't take too much more time with this, but. There we go. So now it goes up and down.
Yeah.
And then I'll come in here. Make a little bulge to put my other piece on.
So that's how you do it. Thanks, Tracy, for a great example of what happened when chemistry met glassblowing. And let's now keep moving and learn how and why chemists and glassblowers working together established melting and boiling points as characteristic values, how microheterotopias made constants of nature. At the start of the talk, I flagged continuity and change as historical problems. Historians like the drama of change, but to me, continuity and stability are every bit as important. In what follows, I want to highlight the making of three kinds of continuity. First, one of place. How can new compounds made in one laboratory, say in Berlin, be recognized and reproduced in others, say London or Madison? Second, one of universality. How do chemical properties carefully standardized by chemists and glassware break free to become the stuff of nature, true everywhere and always? Third, one of skills and materials. This evening, we will see the same person using the same techniques make innovative glassware from the early 19th and early 21st centuries. But I'm going to begin with a change. What I've called the turn to synthesis was a major change in 19th century organic chemistry, a new approach that produced lots of new substances, many of them very similar to one another. And it takes us to the core of the relationship between experiment and theory. The products of synthesis were very hard to tell apart. They often looked the same, near colorless oils or white solids, and they frequently smelled and tasted alike. It was also difficult to know whether a substance made in the laboratory was the same as something isolated from nature. Molecular formula couldn't answer these questions. Formulae remained unstable, and chemists knew that more than one substance could have the same molecular formula, the phenomenon they called isomerism. So formula wasn't the answer, nor was theory, regardless of any prediction it might make. No theory could say what a reaction actually made. The turn to synthesis caused a big problem for chemistry. So big, I've called it the chemical identity crisis. How could chemists know what their reactions made? I've already mentioned some of the characteristics that 19th century chemists used to identify substances, and I've listed them here. I want to highlight just two. Origin was an important characteristic in early 19th century chemistry. For example, the identity of turpentine depended on the kind of tree it came from. But when laboratory chemistry began to make substances that seemed the same as natural products, how was identity to be defined? The second is physiological effect. That's where the dead frogs come in. Most of the natural products that 19th century chemists wanted to make were drugs. Some, like quinine from cinchona bark and morphine from the opium poppy, are well known. Conine from hemlock is better known as a poison. It's what killed Socrates, but it was also used medically. All these substances belong to a family called alkaloids, and they're all quite toxic. At a time when experiments on animals were completely accepted, in fact, they were the cutting edge of medical physiology, it was routine to study this toxicity using frogs. That's why in 1870, Hugo Schiff believed he'd made conine purely based on the way his synthetic product poisoned frogs. You won't be surprised to hear that what Schiff had made wasn't conine at all. But it took him 2 years of hard work to admit that fact, and a lot longer for somebody else to succeed where he'd failed. When Albert Ladenburg finally made conine in 1886, he proved his synthetic product was identical to natural conine by showing that the melting points of their hydrochloride salts were within half a degree. By the 1880s, chemists' way of characterizing substances had changed completely in response to the turn to synthesis. From origin and dead frogs to melting points. But how was this accomplished? 3 chemists took the lead in this story. Around 1840, Hermann Kopp set out to show that chemical composition determined numerical physical properties, including boiling point. Other chemists weren't convinced that composition alone could determine boiling point, perhaps because they were more aware of the complexities of isomerism and chemical constitution than Kopp, who was a professor of theoretical chemistry in Gießen. And apologies to all any theoretical chemists in the room, okay. But Kopp's former teacher and Gießen colleague Liebig saw great potential in this work. Liebig thought boiling points could be useful in identifying organic compounds and in assessing their purity. So when Liebig set his star pupil, August Wilhelm Hofmann, to pioneer synthesis as a new method of investigating organic compounds, Hofmann routinely measured the boiling points of all his synthetic products and shared this data with Kopp. There's a wonderful mutual interest at work there. Kopp needed reliable data to establish the laws he believed linked composition and boiling point, and Hofmann was looking for ways of characterizing the products of synthesis so he'd recognize them if he made them again. 2 chemists whose distinct goals led them to attempt the same thing, reliable boiling point measurement. Here's the problem. It was all very well for Kopp to define what he called the normal boiling point as the temperature at which the tension of the vapor of the liquid is equal to the prevailing air pressure. But because different chemists measured boiling points in different ways, the values they recorded couldn't be compared. As Kopp lamented, what is to be regarded as the boiling point when readings for the same substance made by 2 equally good observers are not in agreement? Kopp solved this problem in glass. Here's the microheterotopia he built to measure boiling point. A round bottom flask fitted with a thermometer and a condenser. He measured boiling points at atmospheric pressure. He used a glass vessel containing platinum wire to prevent bumping, what he called abnormal boiling. Kopp even specified that the thermometer bulb be placed at a particular height below the liquid surface, all part of his efforts to ensure that chemists measured comparable boiling points. Kopp's definition of boiling point in terms of practical measurement as well as abstract principle went hand in hand with a new definition of what it meant for a substance to be pure. Based in part on data produced in Hofmann's laboratory, Kopp learned that pure substances boiled at a sharply defined temperature. Chemists had previously considered substances to be pure when they looked right and behaved right, but Kopp's work established a sharp boiling point as a necessary condition for purity. Let's focus on the thermometer at the heart of Kopp's microheterotopia. Chemists' increasing reliance on boiling points quickly revealed a major problem in thermometry. We think of standards as intrinsic to the devices we use and regulated by national and international authorities, but those bodies were the outcome of exactly this kind of problem. 19th century chemists learned that one of the best ways of making comparable readings was to use the same thermometer, or next best thing, similar thermometers made by the same maker. But what made a good thermometer, and why did some makers produce much better instruments than others? Well, thermometers are complex devices with a fascinating history. You can read more about that in Molecular World. One of the most important 19th century developments was due to Victor Regnault, another former Liebig student. Regnault established the constant pressure air thermometer as a standard or normal device. Regnault's thermometer was constructed with all the resources of Parisian precision science. It was large, complex, and expensive, which made it completely unsuitable for chemical use. That's why glassblowers, including Geissler and Müller, made mercury thermometers like the ones in the photograph. Instruments like this, once calibrated against Regnault's device, also became normal thermometers. So the maker keeps the large precision instrument in his workshop and uses his glassblowing skill to replicate its readings in a mercury thermometer that is itself a microheterotopia. Now, why am I calling a thermometer a microheterotopia? Look at this set of chemists' thermometers capable of measuring temperatures between -10 and 360 degrees Celsius. Each instrument covered a small range, so the chemist could select the right one for the job. Making instruments that were uniform throughout their length was essential for accuracy, but incredibly difficult to achieve. Other problems emerged at high temperatures, which were often required when measuring melting points. Because recrystallization was chemists' best method of purification, they relied increasingly on melting rather than boiling points to characterize the things they made. But at high temperatures, the mercury inside the thermometer tended to decompose, which affected the reading. Geissler solved that problem by introducing nitrogen above the mercury thread to stop it decomposing. And Müller always used this method when making thermometers for use above 200 degrees. Skilled glassblowers controlled the form of the instrument and the chemistry taking place within. Thermometers like this contained a minute other world in which matter was made to behave according to the scientist's will. That's why they were so costly, and it's why I'm calling them microheterotopias. I showed you how Kopp built a melting point apparatus from glassware components. As chemists' reliance on melting points increased, they called on professionals to build dedicated standard apparatus. The picture on the left shows a melting point apparatus made for the Bonn chemists Richard Anschutz and Robert Schulze by Geissler. So the sample was in the inner tube here, inside a sulfuric acid bath in that round bottom flask. Okay, now Geissler's design here addressed two problems. The first concerns that sulfuric acid bath, which was how chemists got to temperatures over 200 degrees. If that bath was open to the air, it exposed chemists to acidic fumes, which was bad. So Geissler closed off the acid bath, except for the air bleed used to equalize the pressure. When not in use, that air bleed was swapped out by a drying tube that extended the viable life of the acid inside, so it needed changing only twice a year. By 1877, Geissler was using glass taper joints to make interchangeable connections between glassware items. The second problem concerned the technical difficulty of measuring high temperatures. If the thermometer thread was cooler than the bulb, the reading required mathematical correction, which was tricky and time-consuming. Geissler's design reduced this problem by insulating the thermometer within the glass sleeve that was surrounded by sulfuric acid vapor. worlds within worlds in glass, microheterotopias within microheterotopias. Now, even this apparatus didn't always ensure that chemists measured comparable melting points. When Ladenburg made conene in 1886, his assistant C.F. Roth worked with Müller to design a new apparatus with an even longer neck. Roth's goal was to eliminate the need for mathematical correction. When he tested his design, he found that melting points that the correction required was just 0.16 of a degree, well within tolerable limits. Melting points measured in Roth's apparatus were now comparable in Kiel, where he was, or London or New York, without correction. This made the continuity of place that I mentioned earlier. Here's what that looked like for conene. The melting point of conene hydrochloride measured in Roth's apparatus was 217.5 degrees, whether it originated from hemlock or was produced by laboratory synthesis. Synthetic conene was identical to the natural product. Ladenburg's synthesis also made conene into dextrorotatory alpha-propyl piperidine, assigning it a three-dimensional structure whose meaning was fixed for any chemist in any laboratory that used standard apparatus and procedures. Chemists and glassblowers used microheterotopias to make the molecular view of organic matter. This work generated a cascade of numerical definitions of purity and identity so robust and widely reproducible that they floated free from the methods that made them. By 1873, when Frank Wrigglesworth Clark tabulated thousands of melting points and specific gravities, he referred to them not as shared standards, but simply as constants of nature, implying their validity everywhere and always. That's my second continuity. Chemistry's quest to understand and control organic nature prompted the discipline's move into glass, transforming how chemists worked and driving advances across the sciences. As they learned to work in glass, chemists called on the skills of glassblowers to build microheterotopias that mediated their control over the molecular world and renegotiated the relationship between the natural and the artificial. This talk illustrated these changes on the small scale, but the same collaboration also reshaped the laboratory as a productive environment for working with other worlds in glass. Just as microheterotopias changed our view of molecules, so chemical laboratories as heterotopias shaped the world around them, a transforming power derived from chemistry's control over the micro world. It's extremely difficult to discover how 19th century scientific glassware was made. It's fragile, replaceable, and ultimately disposable. Chemists sometimes mentioned glassware innovations in print, but this was usually limited to mentioning an authoritative maker. That's why working with Tracy's been essential to recovering this history. His expertise unlocks unique insights hidden in chemistry's undocumented past, and his making knowledge is just as necessary to present-day science. When Tracy and I began planning this talk back in the spring, he told me about a photoelectrochemical cell he'd made a few years back. Tracy built what he calls the Choi cell for Dr. Dong-Ki Lee, a postdoc working with Professor Kyun-Shin Choi, right here in this chemistry department. Professor Choi's group is engaged in a highly interdisciplinary research program developing new electrode materials for electrochemical and photoelectrochemical devices. This cell uses solar power to separate hydrogen and oxygen gases from water, a key method in modern chemistry's search for sustainable solutions to problems of climate, energy, and environment, chemistry is vital in tackling our current global crises. These printed diagrams show the original design that the postdoc brought to Tracy. Tracy's annotations are all over them, and there are many more pages where he worked out how to construct this apparatus. Tracy didn't merely follow the postdoc's design. His skill and material expertise were essential in translating the original concept into a working apparatus. My conversations with Tracy about the Choi cell reminded me of something that I'd learned about Heinrich Geissler. In 1879, Hofmann, then serving as president of the German Chemical Society, celebrated the recently deceased Geissler. That is not the comparison I'm drawing here. Okay. According to Hofmann, Geissler's accomplishments depended on his utterly unprecedented, astonishing lampworking skill, but they were possible only because of the glassblower's profound physical understanding, Hofmann's words. Hofmann's message was clear. Geissler was a scientist in his own right, richly deserving of the honorary doctorate recently bestowed on him by the University of Bonn. Geissler realized scientific visions in ways that amazed those who commissioned his work. Glassblowers like Tracy make a similar contribution today when they realize chemists imagined other worlds in glass. And in this evening's second performance, Tracy's going to share part of the process that he used to make the Choi cell, which when finished looks like this. Tracy.
So when Donkey brought this in, I cried like a little baby inside. There was a lot going on there. And what I want to do is just highlight this little business right here. This was the little bubbler gas exchange. And it looks gonna look like this. I just made some dummy valves. We all know what those look like. We're familiar with those. I just made some because those are expensive. These are the pieces that I'll use. I've got a couple of valves here. So these are all the parts that I'll use to build this piece right here. There's a couple of things, because this is so long, we can't really work it the same way that we did this one. Because of the weight, it would sink down and that seal would start to kink and be unstable. So what we do is we have a little bit of cardboard. When you're working in a company that's, if you had to make 500 of these, you would have a more permanent holder. But because typically what I do is 1 or 2 cardboard is quite effective. So we just put it in here. And we'll use a little holder, a little pusher to push the cardboard in there. What you'll spend some time on, see how this is really crooked in there. I've got one already made that's straight.
Good idea, Tracy. Yeah.
So it's set in there, and now that inner tube isn't going to flop around like it had in this one. So conceptually, we're going to do the same thing we did before. We're going to heat this in, soften it up, and then pull it down. We'd like to just bring it close to the opening at this point. So where before I just used my mouth because they didn't actually have blow hoses in the 1830s, but now we do. This is a piece of tubing with a little rotary elbow on here so that I'm able to blow directly into here. This lets me see exactly what's going on in the fire. Okay. So now we've got it just so there's a nice dome on there. We'll heat it up, and we know that if we heat it up, it's gonna fall down and swing down onto that inside piece. Before I do that, see that little bit of heaviness on there? I want to pull that off. That's gonna fall down into that little hole, and it's gonna have to be taken out. And I'd rather take it out before it gets in there. So now you can see it. It's falling down on there. This is actually called a ring seal. You can see why it's called that. It forms a ring when it falls down on there. And now this just stays put. So I can spend all my time and energy getting that seal nice and clean. I'll pull some of that glass out of there. And I'll blow it open. Come in. Open it up slightly. Now I'll take my valve. I'll stick it on the back side, bring it forward. So now it's stuck on there. And now I'll just tighten up my fire and seal that in. Usually it looks a lot worse before it looks better. That's usually just how it goes. Now I want to pay attention, make sure I blow my hole on the right side. If I manage to blow it on the wrong side, it's one of the beautiful things about glass. All I'd have to do is fill it in and put it where I needed it. So now I'm going to separate the two pieces. I'm going to, because this will get sealed onto the cell. What I'm doing is heating a little band, stretch it, and blow. That's spinning out that glass, and I'll do the same thing. Come over. Heat it up. You can see the cardboard is starting to get a little toasty. Okay. So that'll clean right up. There's a little bit of carbon on there, but that'll wipe right up. Now I'll heat this up and come in here with my graphite and lift this little lip up, and then peel this angle so that then it's ready to go on to the tubing. And don't forget to bend this so that it flows nicely along the bottom of the tube. And you can smell the cardboard.
And that's why you need a glass blower, right? To remember all those bits and get them in place. So Tracy's just demonstrated my third continuity. It is amazing that the person who showed you earlier how to make a microheterotopia from 1900 uses the same skills and materials to make a 21st century device. And here's why those skills are in danger of slipping away from us, as fragile as glass itself. Scientific glassblowers share technical knowledge through their journal Fusion. In fact, Tracy published an article there about the Choi cell. But if we turn to chemistry, the picture is different. The Choi group's work's been published in leading journals worldwide, including several ACS titles and the Sustainable Chemistry journal, ChemSusChem, as well as Nature and Science. I'm getting the burnt cardboard now. But as in the past, those articles don't tell us how the cells were made or by whom. Instead, they offer schematics so that the actual materiality of these devices and crucial aspects of their making are obscure to anyone not directly involved. We're privileged to have access to that knowledge through Tracy, but how will we hold on to it for the future? Who's to count as a maker of scientific knowledge? A pressing question at a time when diversity and inclusion top every agenda. This talk's highlighted the intrinsic connection between chemistry and glass. When chemists and glassblowers collaborate, each brings head and hands to bear on shared problems that standard apparatus can't solve. Chemists can do more when skilled glassblowers realize what they have imagined. Together they build other worlds where fire and material meet to make modern chemistry and transform the world around them. This view of chemistry is embodied in the American Chemical Society's decision to display Liebig's Kali apparat at the heart of its logo. And it offers a powerful reminder that now more than ever, chemistry relies on technical skill and laboratory work, as well as on scientific knowledge and training. Joint creations of glassblowers and chemists, material incarnations of abstract ideas, microheterotopias are simultaneously vital tools in our endeavors to build a better future and a rallying cry for disciplinary sustainability. Thank you so much.